Welcome back. Today is the day we finally put everything together and we talk about the shortcuts that we can use to be able to find the area of a region with the x-axis and a curve from a lower bound and an upper bound. So what does our theorem tell us? The integration from a to b. So if we integrate, I'll write this a little bigger, from a to b of my function f of x dx, we know the integration of little f of x is our big f of x, and then we draw a line and we show that we have an upper bound and a lower bound from a to b is equal to, when we find the value of the function of the upper bound minus the value of the new function at the lower bound. So what is this going to look like? Well, if I integrate from 0 to 4 of x squared plus 1 dx, we've seen this before, haven't we? I think we have. I think we've done this multitude number of times. Remember, we approximated the area using our 4 different methods. We looked at the definition of integration with this function and these endpoints. So now what we're going to do is look at the shortcut of this. So instead of having to find that a plus ci times delta x and all that good stuff, what we're going to be able to do is find the integration from x squared plus 1 from 0 to 4. So we're going to go ahead and integrate this function. X squared gives us x to the third over 3. Integration of 1 is x, and then plus our big C. And we're going to go from 0 to 4, aren't we? Well, what does this theorem tell us? Well, if I plug in my 4 for my x's, and then plug in my 0 for my x's and subtract those two values, I'll get the actual area. So what happens when we do that? So I plug in 4, so we can do f of 4 if you need to, off to the side. So we get 64 thirds plus 4 plus c. If we look at f of 0, here we get 0 to the third over 3, which is 0 plus c. So I'm going to take this answer minus this answer. So what do I have? I have 64 thirds plus 4. If I make this, I'm going to make this as 12 thirds. So I end up with 76 thirds, don't I? Plus c minus, so that's my f of 4, minus, I'm going to take my f of 0, which is going to be just c in this case. So what happens? Well, I have c minus c, which is going to be 0, and I end up with 76 thirds. 76 thirds is all but what? 25 and 1/3 if you reduce it to an improper fraction, which I think we've seen before when we did the definition of integration. And that's what we're going to be looking at today. So can we integrate from 1 to 9 of 2 square roots of x? Well, again, we don't like that square root of x, so we're going to make it x to the 1/2. So I'm going to integrate from 1 to 9 of 2x to the 1/2 dx. Integrating, I'm going to increase that exponent by 1, so 2x to the 3/2 divided by 3/2 from 1 to 9. We're going to clean it up just a little bit. That's going to equal 4 thirds x to the 3/2, isn't it? So I'm going to plug in my 9, plug in my 1, and subtract those two values. So I have 4 thirds times 9. Oh, I didn't put my c in there, did I? Plus c. We'll talk about that here in just a little bit. So there's my f of 9 minus, now I'm going to plug in my 1. So here I'm going to have 4 thirds times 1 to the 3/2 plus my c. 9 to the 3/2, oh my goodness, 9 to the 3/2, 9 to the third power. Do we really want to do that? Of course not. Remember way back in Algebra 2 and pre-calculus, we talked about taking the denominator first, take the root first, and then take it to the power. So here I take 9 to the 1/2. I know that's 3, and 3 to the third is 27. So I have 4 thirds of 27 plus c minus 1 to the 3/2, that's easy, that's 1, times 4 thirds. So I have 4 thirds plus c here. So I have 4 thirds times 27. Again, I don't want to take 4 times 27, but 27 is divisible by 3. That's 9, isn't it? So I get 36 plus c minus 4/3 minus c, and I distribute that negative through. So my c's are going to cancel. That's interesting, because what do we notice up here? The c's canceled as well. 36 minus 4/3. Well, we can do this in thirds if you want. That's going to be what, 108/3. So we end up with 104/3 as our area. So let's talk about that c. What do we notice? If I plug in my c, remember that c is a constant, and it's the same constant if I plug in 4 for my x's or if I plug in my 0 for the x's. That doesn't change that c because there's no variable with that c. There's no variable with this c either. And remember, we'll never have a variable with that c value. So, do we really need this c within any of our problems anymore? And the answer is no. If we have a definite integration, and definite integration tells us that we're going from a lower bound to an upper bound. So if we have these numbers with that integral symbol, we don't have to put in this plus c anymore. Can you? Sure you can. But notice, as I was doing these problems, I didn't put the c in there, and I didn't put the c in here, and I didn't put the c in here. Because in my mind, I've done enough of these that I know if I have a definite integration, if I go from an upper to a lower bound, I won't have that plus c anymore. And you don't need to put it in there either. All right. I do have one more example. It's a little more complicated. It's our integral of an absolute value. So can we integrate absolute values? Yeah, and I'm pretty sure there is a formula for that. Ask me what it is, and I would have not a clue. But when I see this, x plus 1, I know the graph of that is going to look like this, where I have a vertex at -1. And that's a pretty basic graph. We should all know that. So if I go from -2 to 1 here, I have two regions that I've created, don't I? So I can use my integration rules and create two different equations. Because I know that this line segment here, this part of the absolute value, is in the equation y equals x plus 1. This equation is the negative of it. So it's the negative of x plus 1. And that's going to be my y equals. So knowing this information, I can go ahead and integrate this by doing a split integration. So I can go from -2 to -1 of this portion of the function, -x minus 1 dx. And to that I can add the integration from -1 to 1 of this portion of my graph, which is the equation x plus 1 dx. I can go now and go and integrate. I know the integration of -x minus 1. That's -x squared over 2 minus x from -2 to -1. Notice I did not put the plus c in there, not needed. And to that I'm going to add the integration of x plus 1, which is x squared over 2 plus x from -1 to 1. I can go ahead and plug in my -1. So I get the negative of -1 squared, which is going to be +1. So I get -1/2 minus, plug in my -1 there, I get a +1. From that I'm going to subtract when I plug in my -2, my lower bound. So I get -2 squared, which is 4, divided by 2, which is 2, and I have the negative of that, so I get -2. And then plus, when I plug in -2 here, I get 0, don't I? So I get -2 plus my 2 there. Alright, so I end up with just a 1/2. 2 I'm going to add when I plug in my 1 here, so I have a 1/2 plus 1, minus, plug in a -1, I get a 1/2 minus 1. Here my 1/2s are going to cancel, so I have 1/2 minus 1/2, those go away. And I get 1 minus a -1, which is 2, or 2.5, or if you want, 5/2. Now what I want to do, and I want you to be very, 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 please be very careful. I want you to definitely practice this, and when I grade your assignments, I will be checking to make sure you do all that work. But your calculator will also do integrations. And I'm going to go ahead and do that with you to show you how to do that. So if you go to Math, and if you scroll all the way down to number 9, and we call it finite. So function integration. If If you hit enter, it's going to come up with an integration symbol. And it's going to come up with some boxes that you can fill in. You can use this. Be very careful though, because you will have to do this by hand as well. And I will be looking to make sure you did them by hand. But this is a great way of checking your work. So all you do is plug in the numbers. This is going to be a 1, isn't it? And in here, actually, we can go into our math, and we can do our absolute value by going over to num, in our absolute value, and then we have our x plus 1. And then we're going to go ahead and over here, we have to put the variable integration, which is x. Hit enter, and there we go, 2.5. Not sure what's going on with that there, but it's going to be the 2.5 there. And that's our answer. Yay! So that gives you an idea of the beginnings of the fundamental theorem of calculus. It shows you where we can use it, how it's used, how to eliminate that c value, and how to use our calculator to help us out a little bit. Again, it's only going to help us. We have to make sure that we can do it by hand as well at this point. Good luck, enjoy. If you have questions, let me know.